to thank them for their presentation in that we've done a number of scanning efforts at Frank Lloyd Wright Fall of Water. And we can attest to Frank being challenged when it came to uh, reinforced concrete because it's a constant, which is why in the last decade we've done it 3 times because there is a constant. And also, like their presentation, what we're very interested in is the unseen and trying to get at the less obvious, the less visible. Before I move on and know how fast to go, how many people here have used airborne LiDAR? Enough. Okay. How many people could care less about airborne LiDAR? Okay. Then I will spend a little time with it. So the organization of my presentation is just the context issues with the methods being used, a couple of projects examples, and future initiatives. So the context, and again, I'll just fly over that. A lot of what I've been seeing so far, I've been very excited about, but it seems to be from a kind of a heritage standing cultural resource perspective. Well, I'm an archaeologist, so mine is basically going to be focused on remains, ruins, traces, and absolutely nothing there that's obvious. So with that as a perspective, the focus is on landscape archaeology and something that we call landscape phenomenology, which is the architects in the room would know that. And it's basically trying to understand how people perceive and interact with their environments. So where we're working in southern West Virginia, and in outlined in red is the mountaintop mining region. So depending on what you read or haven't read about West Virginia, the Anthropocene, which is basically an explanation of the man-made geologic construct we're in right now, is alive and well in West Virginia. And basically it's alive and well in mountaintop removal mining. So we're working in the New River Gorge, which is a unit of the National Park Service, and a couple of other areas. So with an explanation there, the New River was some of the earliest coal mining in North America, and it is currently an area that's managed by the National Park Service, primarily as a natural resource and cultural heritage park. Then we're also working in the Appalachian Geopark, which is a recent initiative, which is basically right now the UNESCO World Heritage Group has no geoparks in the United States. There are, I think, 2 in Canada, and that's it. And there are actually 2 efforts underway, one in Houghton, Michigan, and the other in the Central Appalachians. So what is a geopark? It's basically where the geologic, the geography has driven the culture that's occurred there, whether it's back to Native Americans or moving forward. And then the third area, which was down south, was Gary Hollow, which is an area that we studied a lot in McDowell County, West Virginia. And it's an area that's been judged to be appropriate for World Heritage status because, again, for over 50 years, it was the largest coal mine in the world. So the region is kind of very rugged mountainous terrain, very heavily vegetated. And that has implications because things left in the landscape will vanish within 20 to 25 years. And then there's just basically hardly any trace. Very rocky, very poor soils. Doing any subsurface work is never going to happen. And traditional fieldwork methods have proven to be very difficult. And again, it's just because of how things vanish relatively rapidly. So the extensive multidimensional effort that we've embarked on, and again, we were doing all that early pre-technology field work, and we were out there just with transits and levels and tape measures and things like that, and it was just a nightmare. So the data collection, it's been a fairly significant effort. So we've collected airborne LiDAR over the entire area, which was basically right around 6 million acres. We have higher density and multi-temporal LiDAR over about 500,000 acres, color and color infrared imagery over the entire area, terrestrial LiDAR, and we're doing a lot now with drone-based photogrammetry. So we have a number of technical issues we were actually interested in. And one of them had to do with a research interest of mine, and that is using anomaly detection methods to find things in the landscape that the rules of the landscape tell us they ought to not be there. Because more often than not in the Appalachians, that has some sort of a man-based influence in it. So what we're doing is we're integrating these technologies with other data. And what we're integrating are basically the beginning point is terrestrial and airborne LiDAR. And so what we can see is an area in which we've done the terrestrial laser scanning in the much larger landscape of where we have the airborne LiDAR. And so now and then, and again, this gets at the kind of artifacts in the landscape I'm interested in are things like those remnants, remains, and traces rather than heritage buildings and things like that. So there are the pre's and there's what everything looks like now. And this is kind of mapping that we did the first time through. It was incomplete. It was not terribly precise nor horribly accurate. So airborne LiDAR is a base for data collection. And what we can see here, and this also is kind of an add-on to my interest, are this, if the post-modern mining had not occurred in that region, this would have been one of the most historically significant small towns in the Appalachians. But it was completely obliterated. So one area that we're actually working with UNESCO on is the impact of mountaintop removal mining in the Appalachians. Should that be a World Heritage consideration, just given its significance? So again, that's just the kind of landscape in which we're operating in. So you can see where the landscape as a backdrop to all of this is pretty significant. So terrestrial LiDAR and the integration of these things. So what we can see is a small mountain community, and we can see where it fits into the larger landscape. So the issues with airborne LiDAR are canopy is an issue, 10 shots per meter squared. And with terrestrial, we hear about hundreds of thousands of points per meter squared. With airborne, it's much less than that. What's important there is we work our way back, and we begin with the density that we want to hit the ground. And then we do kind of analysis back, and we get kind of mid-ground, and then our overall, how much LiDAR data we actually want to collect in order to get that configuration on the ground. And what's important is LiDAR processing is really an art, it's not a science. And what that has allowed us to do was we were able to bypass consultants and contractors and engineering firms because we have our own airborne LiDAR unit. So we were able to gather raw data, which most organizations aren't able to do. And why I said anomaly detection, hunting for kind of human anomalies in the landscape, has proven to be really difficult because anomalies are actually an artifact of airborne LiDAR data collection, whether it's due to climate or rain or just the laser itself. The data that's collected, you're collecting a lot of data that you actually don't want, and it's actually confounding the issue. So what's important there is, again, and a lot of this, if we've looked at airborne LiDAR data, and if you've generated your hillshade in ArcMap, for example, and you've defaulted to the default in ArcMap, don't do that because that's a distance weighted. Use kriging for that because you're going to accentuate the anomalies rather than hide the anomalies like the defaults in ArcMap do. So some lessons we've learned: automating anomaly detection has proven to be pretty impossible. I call it difficult. LiDAR data may be processed to be and appear consistent by consultants, and in fact it's not. So basically what you're doing is masking the quality of the data is what most engineering firms actually do. And automated classifiers don't perform well at all. And it was just things like remains and rocks. You can't tell the difference automated. So, so we also use some other devices. We have a drone that we built from this morning. You saw the GigaPan, and we have this wonderful thing over on the far right. And if you were looking at that and saying, what should that thing be called? Well, it's actually called a wonder pole. And what we do is we put cameras up on that. We've had a laser up on that. We've had a hyperspectral remote sensor up on that. And it just works like a fine. It's awesome. It's only about 20 to 25 pounds, and we can lug it everywhere. So it actually is maybe the eighth wonder of laser scanning and data collection for archaeology. So this was important. So if we're interested in this meshing of airborne and terrestrial data, how do we actually do that? And what are the kind of results that we get? Well, we collect the airborne with what's called RTK GPS, which is basically real-time kinematic, so it's all over the place. We don't use that for the terrestrial. We use what's called static occupancy, where we set ground control points and we just almost make ourselves at home on those points for often a half an hour per point. Then what we do is we register these two things. And then an example over here on the right was every time we do a project where we're going to mesh these two, we will take some swaths and then we compare them and we mash them up. So in this example, it's a 1 meter wide swath. The airborne data we can generally get within 6 centimeters of any ground control and anywhere in the Appalachians, which for our work is really pretty good because we're doing, as the surveyors tell us all the time, at the end of the day, it's just archaeology. So, but then we're able to get our terrestrial data within plus or minus 2 centimeters of that airborne data, which we feel for the kind of work we do is great. And then I also like that slide because the place where we did this was over in Montgomery County, Maryland. And that, in fact, this little structure here is in fact Uncle Tom's Cabin. You might go, say what? Well, it actually is. That's what's the inspiration for Harriet Beecher Stowe's novel, was that little element right there.
I live in Montgomery County. Where is it?
I can get to that exact,
Okay.
that location. It's actually privately owned.
Okay.
So we collect imagery every time that we fly LiDAR, and then and now we're collecting more and more imagery with a drone. The other, I'll go over that. Some of what we found for being very useful is not just the standard ArcMap hillshade, but to generate multiple hillshades, run principal components on that, and then you get all of those hillshades in one hillshade. So tiny little things just basically pop from the LiDAR data at that point. So whenever we're out there, even if it's not a part of the mission, we scan things. That's an early 19th century cornhouse. That's a mid-19th century farmstead. So what we also collect is we collect the all points and the bare earth. And that's because we're interested in what it looks like and what we can discern on each. For example, in the all points, that's the coal loading building. In the bare earth, that's the location of the coal loading building. There's a conveyor going up, an early 20th century conveyor. Over on the bare earth is the location of where that conveyor was excavated for. And these are just some of those objects that we just looked at on the LiDAR with some photos and then a laser scan of those walls. The mine building, which the Park Service reconstructed, unfortunately, and then the laser scans of that Park Service building. I'm a strong believer in just leaving things in the ground, and we don't have to Walt Disney everything. So our work in the Appalachians is farmsteads, the rural industrial landscape, Appalachian mining, and mountain communities, and adaptive reuse and recreation opportunities. So an example again, so this is our terrestrial laser day of getting the 4 or 5 farm buildings. There's that data overlaid on our airborne data. And as we zoom in, we can see within about a 2 centimeter agreement between the airborne and the terrestrial. There's as we move in with the airborne data in the background then. And that's some of our final models. And obvious from the green spheres, we do use targets. And I just don't think we're smart enough yet to not use them. And then we're also integrating kind of interior and exterior where we're looking at the basement of one of those buildings. So drones, we are now, because our airborne laser was about 9 years old and it's an Optec 3100, and Optec this last year wanted $140,000 in annual maintenance. We've decided to put that rascal to pasture. So we're now flying drones. And what we're interested in is combining airborne LiDAR and the structure for motion, or the uncontrolled photogrammetry and structure for motion with our terrestrial LiDAR. So this is a digital surface model from a drone, and what we were interested in this area here, because that's an area that had been very heavily vandalized because of Native American remnants and remains were discovered there about 50 years ago. And there's the elevation model, and we can actually see the results of a lot of the digging on that vandalism, which was not obvious. So we've gotten pretty good at the structure for motion thing. This is Harpers Ferry, West Virginia. And although it's not in that study area, this was the very first time we did it. I was able to generate that model, never having looked at the manual, having no idea what I was doing at all. But it's really not bad. We were able to get in there and measure 6-inch steps and things like that. So the structure for motion holds a lot of promise. Someone in the morning group said, how does the precision line up with laser scanning? Laser scanning is far and away far superior in terms of both accuracy and precision. So then what we were trying to do, we've encountered some problems rectifying our structure for motion kind of natural force with the data from the airborne LiDAR. And we're not sure why, other than you can see when we get out to the corner of an area here, we're beginning to get some drift. And that drift turned out to be about 0.5 meter or so. So we are still working at trying to develop this. And I would suspect it was a matter of number of ground control points. So what we're currently doing is we're supporting heritage documentation. And Gary Hollow, again, is this area that's basically potential UNESCO World Heritage. And so what we've actually been trying to do, and this is just a small part of the time lapse that we've built up for this area. It's still even an area. That's what these towns looked like back in the day. So there's what kind of culture looks like in the all points. So what we were actually interested in was measuring the heights and the configuration of the roof lines of those buildings, trying to do a categorization of these early 20th century mining structures. And just an example of that view back to that same site. So what did we actually do with that? We found that that was one of the greatest concentrations of turn of the 20th century mining community houses still in existence anywhere in the United States. So then we said, well, we probably want to go out and terrestrial laser that. And so that's what we did, and that's what this community looks like. We're also trying to identify locations of potential remains of mining among residential areas. And that's because part of what we're doing is trying to document the impact of mountaintop removal or mining since the 1970s on the loss of historic cultural resources that ought to be important but are lost in the Appalachians. So that's our town of Gary study area. Then that's a 1909 USGS map. So I've condensed this way down. That's an earlier DEM. There's an area where we know back in 1909 there were 3 coal mines. Then we built up a time lapse of that. And again, 3 other coal mines. All of those would have been potentially significant cultural resources if they were still in existence. And this is my poster child for lost resource. And that's just kind of what that landscape looks like. So we're also documenting things that we just find, and it just worked out amazingly. 2 more minutes. A little bit. Is that scanned coke oven and that coke oven are actually the same coke ovens. Now I could say that was a planned field investigation. No. We had the numbers on the coke ovens tied to the historic photo, and there was a plaque right under there with the number of that coke oven. So that was just fortuitous. And because of a personal interest of mine in landscape disturbance, I have an ongoing study in the appellations of iron furnaces. And so there's an example. There's kind of the rough pre-scan of the iron furnace that we get in, and we're able to measure volumes and voids and everything like that. And there's what the data looks like. There we are inside the furnace, and that's the detail that we tried to develop in the rock. An aerial view, and there's that same iron furnace in the airborne data. And then we're also doing some things with the historic bridges and tunnels. I like that graphic because it's a historic railroad tunnel going right through the mountain from the airborne data. So what are we doing with that data on the tunnels and the railroad bridges? Well, right now in the Appalachians, there's a movement underway for rail trails. And if you have a rail trail in the Appalachians, per linear mile, there's going to be an amazing number of tunnels and bridges. And that's what we're trying to document. So what are we doing? We're working on refined documentation of features and sites that have been previously visited, often by us, and we found out with the current technologies that we have how bad our early field work actually was. We're progressing on Gary identifying the status of the historic mine features. And in Gary, we're also historic neighborhoods with significant collections of historic structures, and we're prospecting for new features. So that was it in a nutshell. So